Okay, so am I audible? I hope. Okay, then. So we will start with the second week of the problem solving session for the Introduction to Fluid Mechanics course. And so, in continuation to the topics discussed in the previous week, we will continue to discuss about the applications or the implications of the continuum hypothesis, and then several other important topics such as such as density, bulk modulus, dynamic viscosity, kinematic viscosity, Reynolds number, and non-Newtonian fluids. Then we will briefly discuss some problems regarding them, similar problems that will be asked in your assignments for the week 2, so that solving such kind of questions in today's session will help you to solve the questions that will be asked in your assignment 2. Okay, so to begin with, let's start with the topic of density. So any one of you in the class, would you like to define what density is? Like, what's the general definition of density? Yes, please go ahead.
Mass per unit volume.
Okay, so thank you. That's correct. But if you have attended the lectures by Professor Chakraborty, could you please tell, like, what is that elemental volume that we should take to get a proper approximation or proper approximation to the density of the fluid? Like, what is that smallest volume that we could take, and why? Like, if it's not clear, I can just discuss it, but if you know, you can just go ahead and tell us, like, what's that small elemental volume that is usually advised to take in the case of determining the density of a fluid, in contrast with the elemental size that we usually take while defining a derivative. Say du by dt, we usually say that delta t tends to 0, then the derivative delta u by delta t becomes du by dt, right? So in line with the definition, what's different in this case, in the case of fluid mechanics, while defining the elemental volume that we use to define the density of the fluid? Okay, it's fine. Thank you. I know you understand, but still. The thing is, in the case of fluid mechanics, uh, the volume that we usually take is actually the volume that the volume up to which the continuum hypothesis is valid. Why? Because see, if we go in line with this definition, that delta v tends to 0, and if we take very small volumes, what would happen is, as we discussed in the previous session, that the fluctuations in the value of the density that we will measure will increase if we go below a certain length scale. That is usually the mean free part of the fluid particle. That's why it is suggested that the elemental volume that we take to measure the density should be larger than the mean free part of the fluid particle in that particular flow. Okay, and again, we cannot go to very large volumes, because if we go beyond some certain scales, there is usually some certain length scale, say ls here, that if we go beyond the length scale, the local changes in the local changes in the value of densities would not be captured. That's why ideally the volume that we use to measure density should be small, but not that small that it goes below the mean free part length of the fluid particle. Okay, so that's the crux of defining flow parameters, and this is one of the implications of the continuum hypothesis that we discussed in the previous session. Okay, then another important parameter that we are going to discuss today is the bulk modulus. Okay, so by its very definition, bulk modulus is actually the density, the ratio of the change in pressure by the volumetric strain with a negative sign. Okay, so its definition is shown here, and I am discussing with these things because these are the things that will be discussed or taken into consideration while we are solving our problems in this session. Okay, so it's better to revise the concepts. So if you have any doubt, you can ask, stop me and ask. Otherwise, you can just revisit the lectures so that you can get proper clarity on the concepts. Okay, so this is the definition of bulk modulus and this ratio is known as the volumetric strain. Okay, so we just do some simple mathematical manipulations so that we can replace this volume ratio, volumetric strain ratio to density to ratio of change in density to density of the fluid. Okay, just some minor mathematical modifications so that we can come into a a popular non-dimensional number that could define the compressible nature of the fluid. Okay, so we just take the definition of mass, that is mass is density times the volume, and we take the logarithm of on both the sides, then we take the derivative. From that we get that d rho by rho plus dv by v is equal to 0. So we can just replace this, let me just write it, this delta v by v would be equal to delta rho by rho. Okay, from this definition, then we just substitute this value in this expression. I'm sorry, it's not, we substitute this relation in this equation to get that the bulk modulus is equal to rho del p by del rho. Okay, and in the case of fluid flows, that is governed by the inertia of the flow. Okay, so this terms such as flow governed by inertia, and another could be flow governed by viscosity. Okay, so this statement, flow governed by certain say entity, say inertia or viscosity, so this we will discuss in the later part of the course, like what drives the flow or governs the flow. Okay, like which factor is actually the reason behind the initiation of the flow. Okay, so in this case that we are trying to understand, in our case the major entity that will drive the flow or cause the flow to occur is the inertia of the flow. Okay, that is the inertia of the incoming flow or the initial velocity of the flow. Okay, so that's why I am telling that if the flow is governed by the inertia of the flow, then the pressure gradient is actually proportional to the kinetic energy of the fluid. Okay, I'm sorry, then delta p would be proportional to half rho u square, where u is the velocity of the fluid. Okay, then what we do is we just replace delta p, this relation, into this equation to get that k is proportional to rho by delta rho half rho u square. Okay, then we can just write delta rho by rho is proportional to half rho u square by k. Okay, now from the definition in one of the definition is compressible flow, we get that square root of k by rho is actually the speed of sound in a medium. Okay, so we'll discuss it in depth, this definition, if at all necessary, when if at all we discuss about compressible flow. Okay, so right now we can just consider this to be a mathematical statement. Okay, so by definition this stated that the speed of sound in a medium A is equal to square root of the bulk modulus over the density of the fluid. Okay, so if we substitute this relation in this expression, we get that delta rho by rho is proportional to half u square by a square. Now this ratio of fluid velocity over the speed of sound in a medium is actually known as the Mach number of the flow. Okay, so we then we can write this as delta rho by rho. If we just ignore the factor of half, is actually proportional to the square of the Mach number. Okay, where Mach number is given by u by a. U is the velocity of flow, a is the speed of sound in that particular medium. Or speed of sound, by the speed of sound I would mean the speed by which the disturbances propagate in the medium. Okay, it may sound a bit complicated or confusing, but you can just take this as definitions for right now. Okay, so we are bringing the concept of Mach number or compressible concept of Mach number. We are relating the concept of Mach number to the density ratio of density change in a fluid, so that we can quantify the compressible and incompressible nature of the fluid flow. Okay, that's why, like, if we just take this definition into consideration and consider this this statement. For incompressible fluid, the compressible effects are negligible. Okay, and in that so that in a quantifiable manner, if the ratio of density change to the density of the flow or density of the fluid is less than 5%, then we can ideally consider the fluid to be incompressible. Okay, and just as a conceptual understanding, we would like to differentiate between an incompressible flow and an incompressible fluid. Okay, so just give me a minute, just so that okay, so sorry for the delay. So in the case of incompressible flow, okay, there is no change in the volume of the fluid element. Okay, if the flow is incompressible, there is no change in the volume of the fluid element. But in the case of incompressible fluid, there is no change in the density due to the change in pressure. Okay, so sometimes students, not only students, even teachers might get confused by these two terms, incompressible flow and incompressible fluid. Like, they may sound very similar, and they are actually very similar, but there is a thin silver lining between these two definitions. So that's why the difference in these two definitions of the two terms, incompressible flow and incompressible fluid, are discussed here, so that in near future, like, we can, if at all asked, we can differentiate between these two concepts and just be clear about it. Okay, so now we come into a very important topic, that is viscosity. So from a very vague point of view, we can define the viscosity as the resistance of the fluid against a motion through it. Okay, for example, if you're walking in river, say you're walking in air, like walking in a road. So if at all you want to perceive, you will experience some kind of resistance if wind is flowing in opposite direction to your movement. Okay, so for example, if you're walking in this direction and the wind is flowing in this direction, you will experience some kind of resistance. Of course, if the wind is moving with very high velocity, you will experience some kind of resistance against your motion. Okay, but imagine the same scenario. Instead of walking in open air, if you are walking in a river or in a pond, you experience some greater resistance. right? You find it a bit difficult to move your legs through the water. And in a vague sense, this resistance of motion through a fluid is actually known as the viscosity. Okay, but it's a very vague definition. There can be a very proper mathematical definition that we may consider, but this is what is actually viscosity means. Okay, and this viscosity can arise due to different physical phenomenon. Okay, see, in the case of when we discuss about viscosity, viscosity is a property of a fluid. Okay, and when we discuss about fluid, fluid is comprised of both gases and liquids. Okay, and the origin of viscosity in the case of gases and liquids are different. Okay, though the main agenda or main purpose of viscosity, that is to offer resistance against the motion, is the same, but this origin of viscosity, which is the property of a fluid, is different for both the gases and the liquids. Okay, so I guess this was discussed and emphasized by Professor Chakraborty in the lectures, but let me just try to recapitulate again so that if some questions arises in the assignment problems that we are going to discuss today, we can just correlate our understanding and then solve the problems. Okay, so again, just I apologize for the delay. I will just for a few minutes. Okay, sorry. I'm having a bit cold, so it's very difficult to talk continuously. So it exerts some pressure on my throat, so I'm having to stop in between. Okay, so sorry for the delay. Okay, so let us discuss about the origin of viscosity in the case of gases. Say, okay, so say I would suggest that this is discussed very beautifully and very excellently by Professor Chakraborty in the lectures. You can just revisit it and just revisit the lectures. It would be very helpful. But still, for the sake of this session, I will just like to discuss about it a bit. Okay. So as discussed by Professor Chakraborty, he mentions that in the case of gases, what happens is that if there is a wall, say there is a wall which encounters some gas flow, okay, gas flow over it, okay, and this gas flow would comprise of various gas particles, right? So what would happen is that while there is a wall, the gas particles may get absorbed towards the wall, then after colliding with the surface of the wall, these gas molecules may get ejected out of the surface of the wall. Okay, and if there are and while these collisions they will impart some they will exchange some momentum from a bit there will be exchange of momentum between the gas particle and the wall. Okay, and this exchange of momentum is what being perceived as the viscosity of the fluid, okay, or in this case the viscosity of the gas. So say if this wall is stationary, okay, if this wall is stationary, a gas particle in motion would come and collide with the surface of the wall. Then since it senses in the wall to be stationary, this collision would result in exchange of momentum between the gas particle and the wall, and thus the ejected particle would send a signal or a message to the other particles that the wall that it has collided with is in a stationary state, right? And this exchange of information that the wall is stationary is transferred to the other gas molecules that the initial gas molecule collides after the collision with the wall. Okay, let me just try to draw it. I hope it was clear. I told it in the most easy way possible. So the incoming gas molecule would collide with the wall, then it will get deflected because of the exchange of momentum, and then it would collide with other say, let me just use different colors. It would collide with, say, other gas molecules. Okay, and this collision will again result in exchange of momentum, right? So this exchange of momentum would take place. There would be a series of exchange of momentums. Like again, this molecule will collide with other gas molecules. So on and so forth. So this series of collision is what itself that transfers the message to the other gas molecules that the wall is stationary here. Okay, and this transfer of message that from one gas molecule to other gas molecules is what we call as the momentum transfer. Okay, the transfer momentum. We will come along, we will again encounter similar term while we're discussing about the viscosity in liquids. So I hope that then we will be able to recapture it again, so that we can just correlate what we have discussed right now. Okay, and so this is how the momentum transfer takes place in the case of gas molecules via collisions. Okay, and this momentum transfer itself is a consequence of the viscosity of the flow. Okay, so basically what I'm trying to imply is that in the case of gas molecules, the viscosity or the viscous nature of the fluid is an outcome or a consequence of the intermolecular collisions between the gas molecules. Okay, but in the case of liquids, the origin of viscosity is actually because of the intermolecular force of attraction between the liquid molecules. Okay, so now let's consider the case of a in the case of a liquid. Okay, so again we consider a similar surface, a similar wall, say. So what would happen is that if we zoom into the upper surface of the wall, say here, if we zoom it and put it under a very highly powerful microscope, you will see that there are several crests and troughs, or peaks or valleys, I would say. So the surface of the wall would be very uneven if you look it under a microscope. Okay, and what you will observe is that in these crests and in these gaps or troughs, if you say, there would be some liquid molecules that would get entrapped. Okay, that would basically stick to the surface of this uneven surface of the wall, and these molecules, when they get stuck, what would they do is that since there are several other molecules above them, water molecules above them, liquid molecules to be more general, above them. So what would happen is that even if the other molecules that are above the molecules that are stuck on the surface of the wall, they are not actually, these molecules that are above these red molecules, these are not stuck on the wall. Okay, so they are in motion, they will be moving. Okay, but since there is a intermolecular force of attraction between each of these molecules, so what would happen is that, again similar to the case of gases, these molecules that are stuck on the surface of the wall would impart a message to the above molecules that the wall that we are stuck with is in rest. Okay, we are considering the situation of the walls being at rest. So the wall that we are stuck with is at rest. So what they would ideally do is that they would tend to impart a momentum that will result in slowing down of these above molecules. Okay, of these blue molecules. Okay, so and then what will happen is that, similar to this, since the momentum transfer has resulted in slowing down of these liquid molecule, this molecule will also try to impart a momentum transfer that would tend to speed up this molecule that is stuck to the surface of the wall. Okay, and this series of momentum transfer take place from different layers of these fluid molecules. Okay, so what would happen is that again there are molecules above this surface of this surface of blue molecules as well, right? So again the molecules above these molecules would be in higher velocities, right? Again these molecules will try to slow down those molecules above them, and these molecules that are say, let me just draw it, that are above the blue molecules will tend to speed up these molecules. Okay, so there will be a series of momentum transfer between different layers of the fluid, and that is primarily due to the intermolecular force of attraction between the liquid molecules. Okay, so I hope it is clear now. In the case of gases, the viscosity is primarily due to the momentum transfer between the gas molecules, but in the case of liquids, the origin of viscosity is primarily because of the intermolecular force of attraction between the liquid particles. Okay, so I hope it is clear. Then following that, we come into a very important definition, that is the no slip boundary condition. Okay, the no slip boundary condition. Okay, so we'll just wait for a few minutes so that you can just digest the concepts that we have discussed till now, and then so that we can again take in the next topics, and that is the no slip boundary condition. Okay. Okay, so I'm sorry for a delay. I hope it is clear that whatever we discussed till now is clear. So now we can go on with the no slip boundary condition. Okay, so before discussing the no slip boundary condition, let us just try to discuss. I will not write anything or anything, just try to discuss about what a boundary condition basically is. Okay, so in the case of fluid mechanics, you eventually see that it's actually just a part or an extension of mathematics, and specifically the finding the solution of partial differential equations. Okay, I hope I do not confuse you with some different mathematical jargons, but it's actually important to know beforehand that what we are going to deal with. Okay, so fluid mechanics is basically an extension or a integral part of the mathematics, especially and specifically solving the finding the solutions of partial differential equations. When we eventually discuss, we'll see that the main governing equation for a fluid flow that defines all the fluid flows, that defines the fluid flows for all the Newtonian fluids, is actually the Navier-Stokes equation, which is a second order non-linear partial differential equation. Okay, and for solving these equations we require certain initial conditions as well as boundary conditions. Okay, and boundary conditions basically mean that tells us the value of the solution. Say if you are solving for the velocity of the fluid, then it tells us the value of the velocity at one of the boundaries or both the boundaries of the problem. Okay, so that's why the term boundary condition comes into picture in the case of fluid mechanics. And one of the special case is the no slip boundary condition, which may seem universal in nature because it is in the case of fluid mechanics. If you are ideally dealing with incompressible flows and if you are dealing with liquid flows, then no slip boundary condition is universal in that context. But there are certain scenarios or situations where the no slip boundary condition is not satisfied. Okay, that we'll also discuss. So the no slip boundary condition specifically means that there is zero relative velocity, zero relative tangential velocity of fluid molecule and the wall. Okay, what we've discussed in the case of gas as well as liquids. Okay, see in the case of liquids, what we discussed is that the liquid molecules get stuck in these gaps, these undulations or uneven surface of the wall. The liquid molecules get stuck, and since they are stuck, they impart this message or impart this information to the other liquid molecules that they are stationary in nature currently, and this this exchange of message or information is through the momentum transfer. And this momentum transfer is actually what that tells or imparts the message to other fluid molecules to slow down with the according to the velocity of the wall. Okay, and but the no slip ideally means by its very literal meaning basically means that since the particles are stuck on the surface of the wall, there will be no slip between the liquid particle and the surface of the wall. They are just stuck, right? There's no slip between the liquid particle and the wall of the surface. Similar case goes for the gas molecules as well. Okay, so these collisions that I am discussing, it may sound like the molecules are not stuck on the surface, so there is no slip, but ideally what that means is that like this diagram is a very is a very zoomed in version of what's actually happening. So if we consider in a macro scale or in a practical scenario, these collisions are limited to this motion of gas molecules is, or this collision of gas molecule and then ejection of gas molecule is limited to a very small length scale that is almost imperceivable or unperceivable to a naked eye, or even very strong microscopes as well. It's not perceivable because there are layers and layers of gas molecules above these molecules that are in contact with the wall. So since these molecules are exchanging momentum between the wall and other gas molecules, which are very tightly packed, or although it's not as tightly packed in the case of liquids, but still they are tightly packed enough so that there is an proper, I would say, proper transfer of information from the wall of the surface to the other molecules via momentum transfer, that the wall is at rest. Okay, and so ideally you can consider that these molecules are having same momentum or similar momentum to the surface of the wall, and since the wall is at rest, the molecules colliding with the surface of the wall can also be ideally considered to be at rest because they are imparting that message itself, right, to the other molecules. So that's why this no slip boundary condition is satisfied or acceptable for both liquids and gases. But as Professor Chakraborty has discussed very nicely, that there are some certain scenarios where, especially in the case of gases, that the no slip boundary condition fails to exist. Okay, one of the most popular one is the rarefied gas flows, where there are very less number of molecules to impart momentum transfer. Okay, basically that since there are very less number of molecules, this transfer of momentum is not proper or not ideally done, that results in a incomplete transfer momentum from the wall of the surface. So on the surface of the wall, sorry, yes, from the surface of the wall to the other gas molecules. Okay, so the no slip boundary conditions cease to exist in the case of rarefied gas flows. Okay, basically because the gas molecules are not packed enough to transfer the momentum properly. Okay, and other cases are the phoretic motions, primarily due to thermal gradients or electric potential. Okay, so I don't think we need to discuss it that much, but these are the conditions where the no slip boundary condition cease to exist in the case of gaseous flows. Okay, but in the case of liquids, this no slip boundary condition is more or less universal. Okay, again there might be certain scenarios where these may cease to exist, but I don't think we will be discussing about that in this course at least. Okay, so while I was discussing the requirement or the necessity of boundary conditions, I put along a new term or a new terminology, that is a Navier-Stokes equation. So you will eventually realize how important this equation is, or what is its implication in the case of fluid mechanics. But right now you can just consider it to be a governing equation or differential equation that we try to solve to uh, obtain different flow parameters in the case of a fluid flow. Okay, so numerical equation, and these are applicable, as I told, for Newtonian fluids. Okay, now you may ask, why Newtonian fluids and what is a Newtonian fluid? Okay, see, uh, let me just I guess, okay, so Newtonian fluids basically means these are the fluids that follow the Newton's law of viscosity. Okay, let's write it. Okay, so I think I would again revisit this concept, but let us just let us just discuss. Okay, I guess this part we can skip right now, then just directly go to Newtonian fluids. Okay. Okay, no. I feel like let us discuss the concept of boundary layer and momentum transfer in the case of liquids. So that would enhance the understanding of a Newtonian fluid and what actually we mean by Newtonian fluid. Okay, so I guess that would be an ideal way to understand the concept. So let us go in line of what I have decided to go with. Okay, let us not just skip topics. Okay, so as I told, in the case of liquids, specifically in the case of liquids, uh, there is a transfer momentum in different layers of flow. Okay, so you can consider that near the surface of the wall there is a layer of liquids that are stuck to the surface of the wall. Why? Because there are some uneven undulations on the surface of the wall, and the fluid particles get stuck in these uneven parts, and because they're stuck, they impart this message to the other fluid molecules that are above it, and thus slow down the above fluid molecules. Okay, and these above fluid molecules we will just consider it to be different layer. Okay, so this is the first layer that is stuck on the surface of the wall. Then this layer is just above this layer of liquid. Let me just draw it so it is not confusing. So this is the layer that is stuck with the surface of the wall. Okay, stuck with the surface of the wall. Okay, so let's take u is equal to 0. The velocity of this layer is 0. Okay, and just a minute. Okay, okay, I'm sorry for the delay. So what I was saying is that this layer is stuck with the surface of the wall, so u is 0. Okay, but the next layer just above it, it is not stuck with the wall. Not stuck with the wall, and u is greater than 0. But let me just put the equation properly. There. U is greater than 0 but less than u infinity, where u infinity is the velocity of the incoming flow. Okay, so these terminologies, that is u infinity, incoming flow, inertia of the flow, this we will get acquainted with much properly when we go ahead in the course. Okay, specifically when we discuss about the Navier-Stokes equation, the exact solutions of Navier-Stokes equation, and the boundary layer flow. Okay, and this is actually what boundary layer is. Okay, I will just briefly mention it, but because we eventually discuss it very thoroughly when we discuss the boundary layer. But for right now, just consider what I'm telling now. Okay, so just consider the definitions and the statements, and so that we can capture the fundamental concepts, okay, through these advanced topics. Okay, so as I told, so though this green layer is not not stuck with the wall, but still it feels the presence of the wall because of this layer that is stuck with the wall, and this presence is felt via the momentum transfer, right? Let me write short momentum transfer. Okay, and this momentum transfer is, as I told, there is a series of momentum transfer up till the boundary layer. So this momentum transfer will continue to take place until the uppermost fluid layer reaches the free stream velocity, or reaches the velocity of u infinity. Okay, so I hope it is clear till now. Just take a minute to digest what I have discussed right now. So the concept of momentum transfer, fluid layers. So just take a moment to digest the concepts so that we can just go ahead then. Okay. So, as I mentioned, as this statement said, there must be a mechanism by which the momentum disturbance is propagated in the fluid. Right? This momentum transfer should take place. So there must be a mechanism via which this momentum transfer takes place. Okay. And because of this momentum disturbance, there is a resistance in the relative motion between the different layers of the fluid. Okay. That also is being shown here. Okay, that there is a relative velocity between different layers of the fluid because of this momentum transfer, and we have already discussed what gives rise to this momentum transfer. That is the intermolecular force of attraction between the liquid molecules in the case of liquids, and momentum transfer in the case of gases. Okay, and this phenomenon, right, this phenomenon or mechanism that gives rise to a resistance to the relative motion of different layers of the fluid is actually called as the viscosity of the fluid. Okay, so This is what gives rise to the generation of boundary layers that comprises or includes the majority or the entirety of the viscous effects in the case of flow over flat plate or other streamlined surfaces such as airfoil. Okay, so if you consider this as a boundary layer, okay, then the very concept of boundary layer is to differentiate the two distinct layers of the fluid flow, where one layer majorly comprises of the viscous nature of the fluid flow, viscous irrotational nature of the fluid flow, which is within the boundary layer. It is the viscous effects are significant within the boundary layer, and the inviscid region or the potential flow regions where the viscous nature of the fluid is not that highly perceivable, okay, or the viscous effects of the fluid are almost zero, and that part of the fluid flow can be solved or considered via the potential flow theory. Okay, again these terminologies will be discussed thoroughly when we dive deep into the course, but just to know the implication or the reason of understanding the boundary layer, or how boundary layer helps us to understand the very concept of viscosity and different layers of fluid motion. That's why we have discussed about these terminologies. Okay, so not to get confused with, okay, just simple terms, just take it as definitions for right now. The very physics or the very proper understanding of these terms we'll discuss when we dive deep into the course. Okay, okay then. So say in this boundary layer, at the surface of the wall itself, if we consider a fluid element, okay, just zoom it and then we will discuss it here. So this fluid element, as I mentioned, that the lower layer would be moving with certain velocity, say u, okay, maybe it's not stuck with the wall, it is above the wall, so it has some certain velocity, okay, and the layer above it would move with a certain velocity greater than u by, say, delta u. Okay, why? Because since it's not stuck with the wall, it has a higher momentum or higher velocity compared to the layer that is nearer to the wall. Okay, and this is the relative motion between the different layers of the liquid, okay, or fluid in the case of boundary layer that we just now discussed. Okay, so just a second. Okay, so if we take if we draw a triangle here, like by considering a point that is being displaced because of the relative motion of the fluid layers, if we do a right triangle here, okay, then tan of delta theta, if this angle is delta theta, then tan of delta theta would be u delta theta divided by delta y. Okay, why? Because if you just subtract this by this, you will get u delta theta by, and divided by this length, that's delta y. Okay, now if we take the limit, if delta t tends to 0, delta theta by delta t would actually give us the rate of change of angular deformation or the rate of shear strain in this particular fluid element. Okay, why shear strain? Because the force that enacts on the surface of on this upper surface is via a shear force. Okay, and it is this shear force that deforms the fluid, that results in the deformation of this fluid element. Okay, so say if it's initially it was rectangular, so it will become a parallelogram after deformation because of the application of the shear force. Okay, and so this again would be equal to, if we take delta theta is divided by delta t, so it will become delta u by delta y, where we again take delta y tends to 0, so that we can take this delta terms and convert it into a differential term. Okay, and why we are able to do is, why we are able to consider differential terms? Because of the application or implication of the continuum hypothesis. Okay, these all are correlated. Okay, that's why we built up from the fundamental, right? How the very concept of differentiation or differential terms comes into picture in the case of fluid flow. Why? Because we consider the parameters to be continuous, right? Because we know if the function is continuous, it may or may not be differentiable. But if function is differentiable, it must be continuous, right? So that's why. Okay, and again you may ask why delta theta and why not 10 delta theta? Because right now we are just considering a very small differential displacement. Okay, so if delta theta tends to 0, then 10 delta theta would be equal to delta theta. Okay. So right now again, the rate of angular deformation or rate of shear strain is given by du by dy in the case of fluid element. Okay, in the case of a particular fluid element. Okay, so it's an again now we discuss a very important statement that the manner in which fluid responds to the applied shear force is determined from its constitutive behavior, and this is known as this equation, the tau, the shear stress, is equal to some function of the shear deformation or shear strain is known as the constitutive relationship. Okay, if you just recollect a concept from solid mechanics, it is the Hooke's law. I'm sorry for the delay. Again, my throat was a bit disturbing, so sorry. Okay. So if we just recall the concept of Hooke's law, we just discuss it, draw it and discuss it. So in the case of Hooke's law, we discussed that the x-axis would have the shear strain, and y-axis would be the shear stress. Okay, stress, not shear stress, just the stress. Okay, stress and strain relationship. Okay, so in the case of Hooke's law, what we have that up till the proportionality limit, the rate of shear stress is proportional to the stress is proportional to the strain up till the proportionality limit. Okay, or in some books they define it up till the elastic limit. Okay, but more precise definition is the proportionality limit. So I'll just write it. Okay, so it states that we define color. So it states that sigma is proportional to epsilon. Okay, and again we just write it as sigma is equal to capital E and E, where E is the Young's modulus of elasticity. Okay, this relation between the stress and the strain is known as the constitutive relationship. Okay, similar to that, in the case of fluid flow, the relation between the shear stress and the rate of shear strain is known as the constitutive relationship. Again, same thing. These are known as constitutive relationships. Okay, both for the case of solid mechanics and fluid mechanics. But in the case of solid mechanics, it is the shear strain. But in the case of fluid mechanics, it is the shear strain rate. Okay, just the difference in the this term. Okay, says it is shear strain rate, it is shear strain or shear strain or normal strain, whatever the entity you want to correlate, but this is what it is. So just know the difference. Okay, and again in the case of fluid mechanics, they will again, if it is proportional, then we must have a proportionality constant, right, which in the case of solid mechanics is the Young's modulus. So in the case of fluid mechanics, it is the viscosity, or specifically the dynamic viscosity. Okay, So that is what when we mentioned about Navier-Stokes equation and Newtonian fluids. So the Newtonian fluids comes into picture because most of the fluids that we encounter, or I must say, in an ideal definition, that fluids that are mostly encountered in engineering applications, okay, engineering applications or day-to-day applications, are ideally Newtonian or an approximate version of Newtonian fluids, okay. But there are several fluids which are not Newtonian that we'll eventually discuss. But in the case of Newtonian fluids, the shear stress is linearly proportional to the rate of angular deformation or shear strain, okay, rate of shear strain. So tau is directly proportional to theta, okay. And to remove this proportionality, we use a proportional symbol. We use a proportionality constant mu, which is known as the dynamic viscosity, okay, which has a units of kg per meter second or Newton second per meter square, or more properly Pascal second, okay. And has, in the form of dimensions, it has the unit of m l minus 1 t minus 1, okay. So similar to dynamic viscosity, we again have another definition which is known as the kinematic viscosity, which is basically the ratio of the dynamic viscosity over the density of the fluid, okay, and which again has the units of meter square per second, okay. Okay, so now as I mentioned that most of the fluids that we encounter in the engineering perspective are Newtonian, and that's why we consider that's why we are primarily discussing on Newtonian fluids. And thus Navier-Stokes, the implication of Navier-Stokes equation is very far-fetched because of the fact that most of the fluids that we encounter usually are Newtonian fluids, okay. But again, there are several fluids, several important fluids that we encounter in day-to-day life that are not Newtonian, and the most important one is blood, okay. Blood is a non-Newtonian fluid and thus cannot be solved or understood by the application of Navier-Stokes equation, okay. So by non-Newtonian fluids, what I mean is that in the case of Newtonian fluids, it is tau shear stress is directly proportional to the shear strain rate, okay. But in the case of non-Newtonian fluids, it may not be linearly proportional, but may be proportional to some power of the shear strain rate, okay. So to remove this proportionality constant, again we use remove this proportionality sign, we use a proportionality constant, say k. Then we just do certain mathematical manipulation so that we can just write it tau in terms of shear strain rate to a single power of shear strain rate. So this term k theta dot to the power n minus 1 is considered to be the apparent viscosity, okay. So there is no physical meaning to this term apparent viscosity, but this is just a mathematical manipulation done so that we can correlate this expression to the other expression that we wrote, that tau is equal to mu times theta dot, okay, just to correlate those terms to those equations, okay. So again, then there are different types of fluids that comes into picture when we discuss about Newtonian and non-Newtonian fluids. So in the shear stress and strain rate curve, the Newtonian fluid would be a Newtonian fluid would be a straight line or a identity function curve, where the shear stress is proportional to the shear strain rate, okay. So but there can also be other types of fluids such as ideal fluid, dilatant fluid, pseudoplastic fluid, and Bingham plastic fluid, okay. So I guess these are their examples. I don't feel that I need to discuss it again. So if you're interested, you can just read it about them again in if you want in the different books, or just revisit the lectures. Okay, so now I feel we can start the problem. So I'm sorry, so I will just wait for a while, and I have I have to get the question. So I'll just, it will take some time, few minutes, so just bear with me. Okay. Okay, so I will be back, so just kindly wait. Okay. 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 So I hope I'm audible. I'm sorry for the delay. I just forgot to take the questions in my iPad, so I got I was it took a bit time, but I hope it's okay now. Okay. So let us discuss some questions. So since these are the beginning weeks of the course, so there will be a lot of conceptual questions, one line questions, one word questions. So one word answer type questions. So just to check the concept of the students, that's why. So but again, those are also very important, we cannot disregard them. So that's why just let's go ahead and discuss some questions, and probably some numericals as well, so that we can consolidate our concepts and move ahead with the course, so that we can grasp further uh, complicated or advanced concepts, okay, in the later part of the course. Okay, so the first question is, which among the following statements is or are correct regarding the no slip boundary conditions? Okay, I feel that now it's very simple for every one of you, because we have discussed the no slip boundary conditions very thoroughly. But still, I'll give you few minutes to go through the options and then tell me the answer. Okay. Go to the options. It's quite simple, but still might be a bit confusing, and I guess this is the very purpose of MCQ type questions or MSQ type questions, to confuse the students with similar statements, similar wordings. But if your concept is correct, no one can fool you, right? So just go to the questions. Okay, so for the first question, the correct answers, yes, there will be two answers. The correct answers would be A, that it represents zero relative tangential component of velocity between the fluid and the solid at their point of contact, and that it does not hold true if the fluid is a rarefied gas medium. Okay, so we've discussed this thoroughly in this session, so I don't think I need to repeat it again or go back, but still, if you have any doubt, you can just I guess recap the part that where we're discussing about the viscosity of the fluid both for gases and liquids, and there are special cases where the no slip boundary conditions ceases to exist, okay, or does not exist or fails to exist. Okay, so next question is, which among the following statements is true related to the Reynolds number? Okay, so I don't think we've discussed about Reynolds number in this session, but I believe that we've discussed it in the previous session, and obviously Professor Chakraborty have discussed it in the lectures. So I feel that you can easily answer it. So I'll just give you a few minutes, or not only few minutes, just few seconds or few moments to choose the correct option, then we'll just go ahead with the answer. Okay. Okay, so in the case of the second question, the correct answer would be option B, where Reynolds number is the ratio of the inertial forces to viscous forces. I'm sorry for my voice, my voice is breaking now. And rho v c lc by mu, sorry, mu. Okay, where v is the characteristic velocity of the flow and lc is the characteristic length scale of the flow. Okay, so I'm sorry for my voice, but just bear with it. Okay, I'm sorry for the inconvenience from my side. Okay, so the third question is, which among the following statements is or are correct regarding viscosity of liquids and gases? Again, I will say that we have discussed it thoroughly, but still, I believe I might have skipped this part. I guess I intentionally did that so that you could give some effort to recollect the lectures, but still I will give you some time to get the correct answers and then tell me what would be the correct one. Okay. Okay, then for question number 3, again there are two correct answers. So the first answer is, the correct answers are that for the case of liquids, the viscosity of the liquids decrease with the increase in temperature, primarily because of the fact that the increase in temperature results in the decrease in the intermolecular forces of attraction between the liquid molecules, and thus the viscosity of the liquids decrease with the increase in temperature. But contrary to it, in the case of gases, the viscosity of the gas increase because of the increase in temperature. Why? Because this increase in temperature results in higher number of collisions or higher rate of collisions between the gas molecules that result gas particles that result in the increase in the viscosity of the gases. Okay, so these two are the correct answers. So let's go to the next question. Okay, it's again a very simple question we just now discussed, but still Which among the following is the correct unit of kinematic viscosity? Okay. Okay, I know it's very simple, but I just did a detailed derivation. So again, very simple. I don't think I didn't even required to do that, but still, for my part. So we know that tau is mu du by dy for Newtonian fluids. Okay, and then mu would be equal to tau du by dy. We just take the dimensions of each and every one of them. Then the dimensions of the shear stress would be the similar to the dimensions of stress or pressure or force per unit area, basically that. So it will be ml minus 1 t minus 2 divided by du by dy, which unit would be t to the power minus 1. Okay, so the unit of dynamic viscosity would be ml minus 1 t minus 1. I believe this is a very popular unit that everyone of us must recall or remember, that for dynamic viscosity its units are ml minus 1 t minus 1. Okay, then in the case of kinematic viscosity, we knew that kinematic viscosity is equal to mu by rho. Then just divide the dimensions of rho from ml from dimensions of dynamic viscosity to get that the dimensions of nu would be L square t to the power minus 1, which would be meter square per second. Okay, so the correct answer would be option B, meter square per second. Okay, it was very simple, I know, but I just did it so that you could follow the similar steps for other kind of dimension analysis. Okay, so let's go to question number 5. Again, it's very simple. Which among the following statements is correct for flow over a flat plate? Okay, and I not only flat plate, I would say flow over any streamlined surface. Streamlined in a sense that in those cases the boundary layer is formed, like is very properly formed, and the flow separation is highly delayed. So that's why. Okay, in the case of flat plate, there is ideally no flow separation if the flow is being forced continuously, so there is no flow separation, but still. Okay, so I will give you a few seconds to tell the correct answer. We just discussed it while we were discussing the concept of boundary layer, how it is important, what is primary purpose in the case of fluid mechanics. We obviously didn't discuss the governing equations, but still. Okay, so in this case the correct answer would be option A. Okay, that the flow is considered to be inviscid only outside the boundary layer. Okay, and within the boundary layer it is considered to be viscous, comprised of all the rotational effects of the flow, and outside the boundary layer the flow is considered to be potential flow, and that's why the concept of boundary layer comes into picture. It differentiates the inviscid and the viscid region in a flow, specifically in the case of flow over a flat plate. Okay, or any other streamlined surfaces. Okay, sorry for my low voice that I'm not able to speak loudly because of a throat problem, but I hope you can understand and cope up with that. Okay, I'm sorry. Again, the next question is again very simple. Which among the following is the correct expression for the apparent viscosity? Okay, here K is considered to be consistency index and N is the flow behavior index and U is the velocity. Okay, it's very simple. We just now derived it, so I don't think I should discuss it further. So let us just write it here. It's again very simple. Okay, so for a general relation, constitutive relationship, we thought that tau would be k theta dot to the power n. Okay, then to correlate it with this relation, we'll rewrite this statement or this mathematical equation as k theta dot n minus 1 dot theta dot. Okay, and this would again be considered to be mu a, or theta dot is du by dy, so it simply becomes mu a is equal to k du by dy n to the power minus 1. Okay, so this is the correct answer. Okay, next question is again very simple. There is nothing to it's just a conceptual question. Which of the following statements is correct regarding the pseudoplastic in dilatant fluid? Okay, so I believe that I'll just give you the answers, because something that we should remember, I guess we just now discussed, we just now saw in the case of non-Newtonian fluids. So in the case of, the correct answer would be in the case of pseudoplastic fluid, option C, in the case of pseudoplastic fluid, the flow behavior index is less than 1, whereas in the case of dilatant fluid, the flow index behavior is greater than 1. Okay. I believe we didn't discuss it, that's why I gave the answer, but Professor Chakraborty has thoroughly discussed it in his lecture, so you can just go back and revisit so that you can recollect the concepts. Okay. Again, so which among the following statement is correct regarding thixotropic and eupectic fluid? Okay, so again, these are similar questions conceptual wise. The type of questions, then you need to remember the behavior. So here also I will just give you the answer. The correct answer would be option number A. In the case of thixotropic fluid, the apparent viscosity decreases with increase in time, and in the case of eupectic fluid, the apparent viscosity of the fluid increases with the increase in time. Okay, so that will be the correct answer. Okay, so I just gave you the answer because I didn't find it any like requiring for further analysis, because these are things that the students must remember to solve them. But again, this is a good practice to remember these characteristics, or ideally you can just remember the plots, the strain and shear stress and strain rate plot for different types of fluids, so that you can just and also the examples for different types of fluid that can be also be asked in different competitive exams, or even the assignment questions that might be asked in this week's assignment. Okay, so it is a ideal good practice to do that. But so let's go to the next question now. Okay, so next question is a quite interesting one, so I guess we can solve it together, but I believe that let us just give some time. Okay, so let me just read the question, and I'll give you some time, few minutes to try to solve the question. Then we will just, I have solved the question already, then we will just revisit my solution and just compare the solution. Okay, so let's go to the question. A body weighing 500 Newton slides down at a uniform speed of 2 meters per second along a lubricated inclined surface, making an angle of 30 degrees with the horizontal. Okay, so these are key terms, so let me just underline it so that it is easy for you. Okay, body weighing 500 Newton slides at a uniform speed of 2 meters per second along a lubricated inclined surface, making 30 degree angle with the horizontal. The viscosity of the lubricant is 0.1 kg per meter second, and the contact area of the body is 0.25 meters square. Okay, determine the lubricant thickness assuming a linear, yes, it's also important, assuming a linear velocity distribution. Okay, and this is the thing that we need to find. Okay, so I'll just give you a few minutes to try to formulate the problem, draw the diagram, and solve the question. Okay, it's quite simple. I'll just give you a hint In the case of a linear velocity distribution, you can consider u to be v y by h, where v is your uniform velocity, in this case 2 meter per second, y is the distance from the wall of the plane to the wall of the surface, lower surface of the body, and h is the gap between the two between the body and the surface. Okay, let me just draw it so it's much simpler for you. So if we consider this diagram, inclined surface, this is 30 degree, okay, and this is the body. Just kindly forgive my drawing. And there is a fluid layer between the body and the surface. So if we draw a coordinate axis here, say y and x, then this y is this one, okay, this distance from the surface of the plane to the lower surface of the body, and h is this lubricant depth, thickness that you are asked to find. And this is the problem. I just drawn in the diagram, so I hope it is now much more simpler, but still it can take few minutes to solve it, and then let's discuss the solution. Okay. Okay then, so I believe we have got enough time to solve the question, so let us just go to the solution that I have written. But again, you can just discuss it if there's any doubt. So okay, so again, this is very simple. I have drawn a similar diagram there. So what we need to do is just decompose the force because of the weight of the body into its horizontal and vertical components with respect to the coordinate axis drawn here. Okay, this is the coordinate axis for this current problem. Okay, so this would be the different components of force: 500 cos 30 degree and 500 sin 30 degree. Okay, and mu is given to be 0.1 kg meter per second and a is 0.25 meters square. Okay, and it's given that the velocity distribution is linear. Okay, and this comes through I gave it because this is something that you need to understand. If you are very talented in mathematics, so you will just consider this to be a linear distribution, like you will just approximate it and find it. But ideally this is being found through the solution of a special type of flow known as the coed flow, where we see a linear velocity distribution and this kind of flow where one of the surfaces is moving with a constant velocity, that is what that drives the flow or generates the flow, is known as a coed flow. So keeping that idea in mind, I know the velocity distribution, that's why I gave you the solution, but still you can create your own approximations, but this is the most ideal one, so I have taken this. Okay, which fits in well with the current problem. Okay, so we know that tau is a shear stress, so it will be the shear force per unit area, and we know that a is 0.25 meters square, right? So just replace it here to get f by a is equal to mu v by h. And how we get this? Just replace u here to get that du by dy would be equal to mu v by h. Okay, simple. Sorry, du by dy would be equal to v by h. Okay, mu is already there. Then again just mathematically manipulate it to get, because this is a quantity that we need, so h would be equal to mu va by f. Just substitute the known values here to get that h is equal to 2 into 10 to the power 10 to the minus 4 meter or 0.2 millimeter. So the correct answer would be option D. Okay. Okay. So the final question is from the following test data, determine the bulk modulus velocity of water at 3.5 meganewton per meter square. The volume was 1 meter cube, and at 12 meganewton per meter square, the volume was 0.99 meter cube. Okay. So this question is again very simple. So by definition of bulk modulus, we know that it would be delta P by minus delta V by V. Okay. So here all the terms are just given. So delta P would be equal to P2 minus P1, because of the increase in pressure, the volume of the fluid has reduced, or fluid is compressed. So you can just write here V2 minus V1, and the initial volume is V1, right? Just substitute the values now. So P2 would be 12 into 10 to the power 6 minus 3.5 into 10 to the power 6 Newton per meter cube, sorry, meter square, and divided by minus of 0.99 minus 1 divided by 1, right? So if you solve it, you will get that k is equal to 0.85 into 10 to the power 9 Newton per meter square. Okay. So the correct answer would be option number B. Okay. So that's all for today's class. I hope I was able to clear the concepts regarding density, bulk modulus, Newton and non-Newtonian fluids, and viscosity. Okay, these are very fundamental topics, but still, by the very word fundamental, it does not mean it is easy, but fundamental means it is a building block of the course that we are going to undertake. So just you have to be clear with all these fundamental concepts, so that we could now build upon these concepts and move ahead with the course smoothly. Okay, so there will be many instances where the very fundamentals of your understanding on fluid mechanics will be questioned by in the assignments, even while we're discussing the advanced topics. Okay, so at that moment I believe that none of you should encounter any confusion, but rather be quite clear on your fundamental understanding of the course. Okay, so I request you to emphasize more upon these fundamental concepts, especially for the first 2-3 weeks, so that you are comfortable with the basic terminologies, and then you can easily grasp the advanced topics that we will discuss without having to go back or look again or revise these concepts again. Okay, this should be just embedded in your brain. This concept, this terminology should be embedded in your brain with the proper definition and understanding, so that the course could be understood and taken smoothly. Okay, so with that I feel that's all from my side for today's session. If you have any doubt, please kindly consider to attend the lectures by Professor Chakraborty. Like, they will be the best sources of knowledge and information for you as well as us to understand the course and the concept and the subject. And But nevertheless, if you have any doubt, you're most free to, you're most welcome to put your doubts in discussion forum, and we're gonna again discuss it in the next week. Okay, so thank you, and that's all from my side.